back to my YouTube channel. So, welcome you to the series of DSP Lab. Okay, DSP Lab. So, now in this series, now we are continuing with uniform quantization and PCM, which is your pulse code modulation using Python code in Google Colab. Okay, we will implement a uniform quantizer from first principles, generate binary PCM code words, and measure the mean squared error across different bit resolutions and verify the classic 6.02 n plus 1.76 decibel rule for signal to quantization noise ratio SQNR. Okay, so now before running the code, let's review the mathematical background. We use a full scale sinusoid normalized to the range, that is your -1 to +1 volt. Its average signal power is px equal to a square by 2, which will be your zero point 0.5 watts. Okay, so when quantizing with n bits, we divide the range into L equal to 2n equal in intervals of step size, that is delta equal to 2 by 2, and assuming the quantization error is uniformly distributed between minus delta by 2 and plus delta by 2. The noise variance is PQ equal to, you can say, delta square by 12. Then calculating the ratio of signal power to noise power yields the standard equation SQNR is equal to 6.02 n plus 1.76 decibel, which I have earlier repeated also. So for mandatory validation in this experiment, every generated index must fall in the range 0 to L minus 1, and all binary PCM code words must exactly and bits long. Okay, so now just go through the Python code. So let's look at the Python code implementation in the Google Colab. Okay, so in our uniform PCM quantizer, you can see here. Okay, uniform PCM quantizer here. You can see we calculate the integer using np dot x minus x minimum by delta. Just 1 second, let me find that line. Aha, here is that np dot floor line. Here is that. Okay. Where is that line? Where is that line? Where is that line? So here is that line. Okay, here is that line. So now we generate the binary PCM stream by formatting each index into a binary string with width n. Okay. So we asset validation tests directly in Python to ensure every index and code word matches the theoretical constraints. We evaluate bit resolutions for n equal to 2, 3, 6, and 8 bits. Okay. Visualizing the results. Okay, now. So here our simulation outputs. Okay, here is our simulation output. I have already done it. So you can see for here original versus quantized waveform. You can see that for n equal to 3, the staircase shape is clearly visible. You can see that is the red one. This So as we increase n equal to 6 now, so the reconstructed waveform closely tracks the continuous sinusoid. Okay, so now go to the second one, which is the your which is your, you can say that the staircase characteristics. This plot displays the non-linear transfer function showing discrete decision boundaries and output steps of a height, that is delta equal to 0.25 volt. Okay, so now go to the third one. You can say here. Okay, so go to the third one now. The error signal ET oscillates strictly within plus delta by 2 to minus delta by 2. Okay, showing significant reduction as bit depth increases. So now go for the fourth one, which is your histogram. Let me zoom it little bit. The error distribution over 10 sinusoidal samples is bounded between minus delta by 2 and plus delta by 2, you can say. And for the fifth one, the SQNR versus bit. So you can see that the red curve represents our simulated measured SQNR, and the dashed blue line is the theoretical 6.02 n plus 1.76 decibel per. They align very closely across all tested bit depths, verifying that each additional bit yields a 6 decibel of improvement. Okay, so now in summary, we can say that in 1 second, we can say that Increasing bit resolution exponentially decreases quantization step size by delta. Okay. So the experimental SQNR verifies the theoretical 6 dB per bit rule. Okay. So the Google notebook and full lab report are uploaded to my GitHub repository linked in the description. So if you are interested, then you can obviously check those, and please feel free to ask if you have any query about this video or about the lab. So I am always there for you. Thank you everyone.